Hello and welcome to Ubiton AI Labs. My name is Sándor, and in this episode we are going to implement a convolutional autoencoder. Nothing crazy, but it's good to get a feel of the stuff, and I will explain what an autoencoder is and how convolutions work in PyTorch. So an autoencoder is a neural network that compresses high-dimensional input data into much lower dimensional so-called feature vector in a latent dimension. What does this mean and why is it useful? So basically the network architecture, imagine that you have an image, a pretty big image, and you feed it through a neural network that layer by layer starts to get smaller and smaller, and eventually it arrives in a space that has a much smaller dimensionality than your input image. So if your input image has like 20,000 pixels, this latent space can have only 1,000 dimensions. And in order to create this autoencoder, how you train it is that you have a decoder that layer by layer extends. And you train the decoder and the encoder together to be able, for example on images, to be able to reconstruct the input image. And this bottleneck in the middle basically ensures that the compression happens. And after this encoder and decoder is trained, you can separate down the decoder and use just the encoder part. So for example, if you have a video or video frames, sequence of video frames, you can take this encoder part and feed the frame into it. It will compress into a much smaller representation, and the rest of your huge neural network can work with that small representation instead of the huge input image. Obviously this saves compute, it's much higher performance, and lots of state-of-the-art autoregression models use it. Now, no worries, the autoencoder that we will implement has been around for a long while. It's not a new model, it's nothing crazy, it's a pretty simple model, and it's actually not useful in itself. A variation of it is used in state-of-the-art models. We will just implement a basic autoencoder, and later we will build on it and implement a vector quantized variational autoencoder that is actually used in Gini and lots of other very high-end state-of-the-art models. So this I aim to be a fun exercise, not too complicated exercise, but a very useful one for later future work. Enjoy! Alright, so let's get to implementing our autoencoder. You can just create a new Python notebook. If you don't know what that is, then you can install a Python extension in VS Code, create an IPyNB file, and you need to set up a conda environment and install Torch, which itself will install its own CUDA version, so you don't need to separately download and install CUDA. We will be using Python 3.12. And disclaimer, I'm not entirely implementing this from the top of my head. I have created a learning material, which I will make available in the Skool Community. But basically, if you follow this line by line, then by the end you will have it ready for yourself. So let's start by importing the libraries that we will use. So as you can see, data loader is basically a nice utility that you can use to basically sample your data set. We will download the Cypher10 dataset, which consists of 60,000 32 by 32 RGB images. it's not too tiny, but it's not so large that you cannot train it on your own GPU at home, so you don't need to rent high-end GPUs from the cloud. And later, of course, if you want to customize your model, then you can use a bigger data set. If you can still train it at home, fine. If not, you can rent some bigger GPUs in the cloud. So we also need the Torch Vision library. You need to install this separately, I believe. And its transforms. Import it as T. Hope you can still see it. Before going anywhere further, we don't really want much randomness in our executions. So we have to fixate the seed, the random number seed that Torch uses. You can enter any fixed constant number here. This will ensure that between runs, our data mostly stays the same. It doesn't make the environment entirely deterministic, but it helps a lot with that. So, before we can get to implementing neural networks, we need the data set. We will actually have the Cypher10 split into a trained data set and a test data set. The trained data set consists of 50,000 images and the test data set consists of 10,000 images. We will train our model obviously on the trained data set and we will evaluate it on the test data set. So Torch Vision provides these image data sets. You can see Caltech, Cypher 100, and we'll use Cypher 10. The root is where Python will download the data set, so make sure you have a few gigabytes of free space. And let's just make it data sets. With this parameter, we indicate that we will pull only the 50,000 images for our training. And we will have another one of this where train is false, and we will use that for testing. Now, we want to download it in case it's not located in the datasets folder. If it's already downloaded, this will not be downloaded, so you can safely run it multiple times. And one more thing. We need to provide a transform. And the transform is basically not totally necessary in this case, but it's a good practice to always declare your transforms, because for training, you have access to various transformations, for example, color jitter, random horizontal flip. So for training, it's good to randomly flip the images, so the neural network learns how to generalize and not just learn, for example, that a cow is basically a cow that always faces to the right, because during the learning phase, many thousand iterations, it will come across with cows facing left, right, and you can even vertically flip it, but an upside cow is, well. So we have our train data set. Now let's pull our test data set. Let's set this as false. So this is cool, but we actually need to sample this data set. So for that, we will use the data loader. And as you can see, you can provide it as the first parameter, train data set. Now the batch size since the training needs to run in an optimized way, memory copies from disk, RAM and VRAM will happen in batches of images. So when we run inference on the model and then calculate the loss backwards and then adjust the gradients, it won't pull the images one by one because that would be really slow. VRAM is larger, so we can choose a batch size depending basically on how much VRAM you have. You have to experiment with this. Generally, larger batch sizes lead to better outcomes. For now, let's declare this as a global variable and just stick to 64, which should be fine for most modern GPUs. Here is a nice trick. Data loader is really nice because you don't need to deal with randomly picking images into your batch. You can just set shuffle parameter to true, and when you iterate through the data loader, it will throw batches out randomly sampled from this trained data set. This is also great because when you shuffle, let's say if you didn't shuffle, your model will would start to learn that these images that they actually have some correlation between them, but that is not true because our samples are independent of each other. So by shuffling and randomly picking images into each batch, we can make sure that the model won't learn any correlation between our independent samples. And a few other parameters to make the data loading a bit more efficient. This is just for performance. So this will be our train loader. Almost exactly the same for our test loader. But we don't need to shuffle when we are running the tests because we are not learning anything there, so it would be just redundant. Okay. So we have our data loaders. Better to call this load data. And now it's downloading. Meanwhile, we can continue our implementation with the encoder itself, which will be a neural network module. This is the skeleton basically for every modules. So we can create our decoder here as well. And now get to the specifics. So as I said, the encoder takes as input this image, in this instance from Cipher 10, which is 32 by 32 by 3 color channels, and it outputs a latent vector in this latent space with a much lower dimensionality. So our input image is 3072 bytes or numbers, because 32 by 32 is 1024, by 3, 3072. And we will experiment with what latent dimension is the best, but it's going to be a lot less. So for example, our latent dimension could be 256, which means that more than 3000 numbers get compressed into 256 numbers in this lower dimensional space. So we'll have a sequential neural network, which means it passes information layer by layer. And before going any further with the init method, let's just get rid of the forward, because that's much simpler. What we will do with this sequential model is we will just call it like this with the input. And here the input is the image itself converted to a tensor in the shape of 3 by 32 by 32. That is channels by height by width. That's the shape of X here. And this X is passed into our encoder, sequential neural network. So we will perform a convolution, and the input channels are 3 because it's an RGB image. Now the output channels is basically how many filters we have in this convolutional layer. Let's just say now it's 64, and I'll get back to this in a moment. The kernel size is 3, stride is 2, padding is 1, and that's what we need. So what do these parameters mean? So the kernel size means that the convolutional filter will be a 3 by 3 matrix of numbers that basically pass through this image, convolve it, and the stride 2 means we don't step 1 pixels with this matrix and multiply the numbers. We step always 2. And with a 1 padding, this results that the 32 by 32 image in size gets reduced to a 16 by 16 image. And we have 64 of these filters. So 64 3 by 3 kernels go through this input image, and each kernel has 9 parameters because it's 3 by 3. And we need to pass a non-linearity to this. Let's use a ReLU. It's pretty sufficient for our purposes. Now for optimization, we can set it in place so it doesn't allocate new memory, create new tensors, which is fine for our case. So if the previous convolution reduced our image size to 16 by 16, this will reduce it further to 8 by 8 and then 4 by 4. However, the input channels here are not anymore 3, because those 3 input channels get replaced by the number of the kernels from this pass. So what this means is that we have the 3-channel input image. Now after this pass we will have 64 3 by 3 matrices called kernels that contain some information bytes in the form of bytes, basically. And if I just want to extend it here, like this. And the good practice is that when you apply the convolutions, you increase the number of kernels as you go deeper and deeper into the network. Generally, the first few layers, you can look up some VGG16 and other older deep convolutional neural network models. The first few layers start to learn the most primitive features in an image, like lines, edges, in various orientations, etc. And as you go deeper, this 128 kernel, 128 number of kernels will have as input the 64 kernels from the previous image. So if those are lines and simple shapes, then this will start to kind of package them together. So from simple lines, points, edges, corners, it will start to assemble more complex shapes, like half of a square, triangle, maybe not that complex in the second layer, but kind of as you go deeper, the shapes start to get more complex. Because if you look at it that way, it hierarchically builds up these shapes from very primitive ones to very complex ones. And if you have larger images where you can, because for example, if this was 1000 by 1000, you could apply lots of convolutions, even with stride 2, and it would be a really deep network. And you could extract the weights from that deep layer, and you could see that it learned to recognize faces, dogs, complex shapes of animals, etc. However, a convolution doesn't necessarily need to reduce the image size. So if I was to set a stride 1, which I believe is the default parameter, it would keep the size of the image. Probably we would have to adjust the padding, but if you exactly want to know what will be the shape of the tensor after a convolution, then you can debug it easily by I don't have a comment feature on Windows, but by commenting out the other layers, running the encoder on some arbitrary single image, and printing the shape of the tensor. And we will do that in a bit. But for now, we apply 3 convolutions, end up with a 4x4 image. And now the shape is, at this point, the shape is 256 by 4 by 4. This is the shape of the tensor that is outputted after this convolutional layer. We need to add another linear layer. This is basically a fully connected layer, a matrix. Now, as you can see, the input features, the type is an int. It's not a shape. So this is the shape of the tensor, and we can flatten it. In this case, the shape will be this number evaluated. So that's 1024 by 4. If I'm not mistaken, that's let's write it like this. It's maybe more understandable. So now we have a flat layer of more than 4,000 neurons. Just for demonstration, this will evaluate to that 4096. Right, so that's the number of input features from that image. And we will project this into our latent space, which has how many dimensions? Latent dim. And that's basically the encoder. Now you may ask, how do you really calculate the size of the image after you perform a convolution? And this is basically the equation. But you can also just experiment with the kernel size, the padding, and debug it by printing the shape of the resulting tensor. So the input size in this case is 32. The padding is 1. So that's going to be 34 minus the kernel size, 3. So the numerator becomes 31. The stride is 2. And we floor it. These pipe-looking stuff is the flooring. So that's going to evaluate to 15. This big term. Plus we add 1. So the output size is 16. I'm just going to rewrite this to 2. Don't forget to write it back to 2. And so we continue to downsample our image and thereby compress it and force the neural network to learn those features that I talked about previously. So this is another operation that we will use for the decoder. It's transposed convolution in 2 dimensions. What this does basically, with this you can upsample your image. It's kind of an inverse convolution, kind of, not completely, but you can think of it as something like that. So decoder will be mostly the same with a small twist. So after our linear layer completes execution, we will end up with a one-dimensional vector with more than 4,000 components in it. That will be the input, x here, for the decoder. So in that case, we will use another linear layer from latent dim and similarly, as we kind of downscaled it, we will upscale it back to the same size. And we have similarly an unflattened function. The current dimension is 1 because it's a one-dimensional tensor. And the unflattened size, and this is why I wrote it like this. It's going to be 256 channels, 4x4 image. Basically, we just reshaped our 1D tensor from a vector of more than 4,000 components into a 3D tensor with 256 channels, 4 height and 4 width. Now we can use conv transpose 2D, and the in channels will be, of course, 256. And as you see, we added more and more kernels as we got deeper and deeper into the network. And as we go outside to our output, here we will start to reduce the number of kernels. So it's as we were, but in the opposite way. And here is the trick now. Here we need to use kernel size of 4. This equation explains it. Conv transpose is a bit different than conv 2D, and you can substitute it. You can go and actually look at this explanation. But in the end, if you're uncertain, I always say you can just execute it and print the shape of the tensor so you can set the sizes properly. Let's use another non-linearity here, a rectifier linear unit. And now we have one layer, so we can multiply it and upscale our image back to 32 by 32. Great. The number of channels returned by this conv transpose 2D was 128. So that is the number of input channels here. And we further reduce it to 64. And in the last one, since the resulting image size will be 32 height and 32 width, we need 3 color channels, because we are reconstructing the same image. And one more thing, in the output layer you cannot use a ReLU, because a ReLU, if you look at the graph of it, isn't going to output a number between 0 and 1, which we need for our tensor. It has an indefinite output, and it's much harder to learn for the network to compress the ReLU's output into between 0 and 1. So it's just much easier if we already use an activation function like the sigmoid, which by nature has an output between 0 and 1. This is it. This is basically the core of the autoencoder. An encoder that compresses the image based on learned weights into the smaller representation, and then a decoder reconstructs that same image from that latent representation. So before we continue, I would like to make a fix, because nn.sigmoid doesn't support the in-place parameter. So let's just remove that. And we could test our encoder and decoder and see if they are compatible compatible with each other, in the sense that if the encoder receives an input image of a given size, encodes it, and then the decoder, when it decodes it, the output should be the same size. So we should check if our conv transpose 2Ds actually upsample the image to the same size. Now let's scroll up, and we can copy the test data set from here. And let's create an instance of our encoder with some random latent dimension, for example 400, and create a decoder with the same latent dimension. Now the Cypher10 dataset contains pairs of inputs and outputs, and the inputs are images, the outputs are labels. For example, the input is an image of a cat and the label is a cat, like literally the string cat. So we won't use the labels because what we are trying to do here is reconstruct the input image. So we have an image. We have an image and the label that we don't use. And you can set any number here up till 10,000. It's random. So let's try to print the shape of that image. It's not an image anymore because, as you can see, the transform here, it converts to a tensor. And the RGB values are between 0 and 1. So let's run this code. It gives what we expect because it has 3 channels, RGB, and the size of the image, the height and the width. Okay, cool. Now let's use our encoder to encode this image. Let's call this image ants. And we run into an issue. Why? Because PyTorch NN modules expect the inputs in batches. And this is a single image. So we have a shape of 3, 32, and 32, a 3-dimensional tensor. But what we actually need is, for example, if our batch size is 64, then we need a tensor in this shape. So actually 64 pieces of these image tensors. So how do we do that? In case of a single image, we can use the function unsqueeze. And it will expect, it will basically insert a dimension into the location wherever you want. So in this case, I want to insert a new dimension into the 0th location. And this will change the shape of the image into 1, 3, 32, 32. So it will just insert the one here. Now we can encode our image. And that means image enc this is the batch size here, in our case 1. And 400 is the number of components in our latent vector. So image enc is our latent vector. Remember, we haven't trained our model yet, so it's going to be basically random, but we can see the shape is fine here. So our encoder, shape-wise, it's okay. Now let's try to decode that image. And print its shape. One image, 3 channels, 32 by 32, so that works. Now let's talk about the 2D convolution operation itself in PyTorch, because it can be pretty confusing at first. So Let's print our encoder's first layer's weights. So this layer's weights. This doesn't say a lot to us, but if we print this shape, you can see that it's 64 by 3 by 3 by 3. How is that possible? So, as we wrote here, and I expanded this a little bit, because when you write kernel size equals 3, it actually means 3 by 3. So that's fine because it's here. And we have 64 output channels. That's also fine. But what's this 3 doing here? That's basically the number of input channels. It's a bit confusing because PyTorch cores, you set kernel size here, but the kernel size in fact will be a 3 by 3 by 3 tensor, because the convolution is performed for each layer. And how is that convolution performed? I've taken this image from Geeks for Geeks. It's really illustrative. We have our kernel, which here has a depth of 1. So it's not 3 by 3 by 3, it's just 1 by 3 by 3. And as you can see, here is this yellow highlighted area on our input image. Let's assume this is a grayscale image, and we're performing convolution on this grayscale image. As you can see, the number 1 here on the top left corner is multiplied by the number in our kernel. We can also call the kernel here as a filter. It's multiplied by 0. Then we multiply the number 5 in this column with the number -1 from this column. And number 9 here with 0 from this column. And then we continue with the next column and the next column. And we basically perform an element-wise multiplication and add those numbers together. When we have a bias, in this case 5, the bias is added to this sum. And so for the first convolution, in this example, we will end up with the number 11. And as you can see, the output image will be smaller, because as you slide this window through the input image, it will reduce its size. However, we have defined the padding 1 here. What does that mean? In this case, PyTorch extends the image in every direction with a column and a row in the beginning and in the end, so around basically, by default with zeros. So you don't start a convolution actually here, you start it, so if this highlighted area has the 6 in the center, the first convolution with padding, then the number 1 would be in the center. Then you slide all this through with a stride 2, which means you jump 2 cells to the right, 2 cells to the right, not just 1. The default value for a stride is 1. And with stride 2, with a padding 1 and a 3 by 3 kernel or filter, the output image will be reduced to half of its size. So under filter, to clarify it, I mean this 3 by 3 matrix. And the kernel itself is a 3 by 3 by 3 tensor, because we have 3 input channels. And for each input channel, this filter will convolve, will slide through the whole image and convolve it and produce an output. Let's print out the output size of this same first layer. So actually the first layer is addressed enc.enc 0th index is the first layer. We pass in our input image, it evaluates, and we print out the shape of the output. So as you can see, 16 by 16 is fine. As I said, we downsampled our image and it's half of the initial, and we have a 64 batch of these 16 by 16 images, also called feature maps. Why 64? Because we said that our output channels, or number of feature maps, should be 64. Now, to play around with this a little more, to make you more understand this, let's import torch.nn.functional as f. And let's create an example image. In this case, let it be img torch.tensor. Actually, let it be torch.arrange. Let's create a 5 by 5 image. That means we will have 25 values. And if we print this, you can see this is just a single vector of 25. But we can view this single vector of 25 as a 5 by 5 tensor. Cool. Now this is our input image. These are the values of our input image. So let's just imagine that these are values for grayscale pixels. So for example, this is completely black and this is somewhat whiter. And let's define a filter, or let's say kernel. Pretty much the same way, but it should be a wee bit smaller. For example, 2 by 2. Then in total we have 4 values. Print our kernel as well. So we have 0, 1, 2, 3. Great. Let's apply the convolution. Convolve this input image with this kernel. We can do that with f.conv2d. The input is the image. The white is the kernel. And let's just leave a 0 BIOS and 1 stride for now. Let's see what it says. Error. It's because conv2d expects the input in the following shape. Here this is basically the number of images, the batch size. And the second number is the input channels. For now we have just one input channel, so it is safe to prefix our dimensions with 1 and 1, and the same goes for the kernel. It works. Great. Let's print it out. The shape is 1 by 1 by 4 by 4. And the output itself is this value. So how does this come out? 29, we multiply, I'm going to write it here, we multiply 0 with 0. Then we multiply 2 with 5. Then 1 with 1. And then 3 with 6. So we have 11, 18, it's 29. So as you slide this through, it will basically result in this output. Cool. Now, well, as you can see, our input image was 5 by 5. The kernel was 2 by 2. So the end result is 4 by 4. Then let's assume our image has 3 channels. And our kernel, in this case, also has to have 3 channels. For the sake of this example, at least. So let's assume this is the red channel in the input. This is the green, and this is the blue channel. This kernel is for the red channel. So the convolution is performed on the red channel with this kernel, or this filter. It's better to say filter because there's 1, 2, 3 filters in this kernel. So correspondingly, this filter will convolve the green channel, and this filter will convolve the blue channel. But as you can see, our output, it doesn't have 3 channels. It only has this internal matrix, which is a 4 by 4 matrix. So how is this possible? It's because PyTorch internally, it performs the convolutions channel by channel, and then it adds them up in this way. So let's say the convolution result for the red channel is out R. Then it adds out G, out B, plus the bias, if we have it. This is the final output that you see here. In this case, we didn't have a bias. So what this means in practice, that our output will be a 16 by 16 feature map, actually 64 16 by 16 feature maps. So this is how the convolution 2D layer works in PyTorch. But what is this conv transpose 2D? So we notice that we can downsample an image using a convolution, and here we are upsampling those images. So basically what conv transpose 2D does with the stride 2 is that it first upsamples the image, inserts zeros to every second element in our image. I will explain this illustratively in a bit, and then performs a convolution. So for example, if our input image is 1, 2, let's make it a bit bigger, 3 by 3 input image with some random values. If we set stride to 2 in conv transpose 2D, it will insert zeros to every second column, and also every second row. This way it upsamples the image and then performs the convolution with a stride 1. And you can see the calculation here. We also add the padding 1, which means we can further extend this around with zeros. Then for this kind of input, we have to choose a kernel size of 4 to actually upsample the image to double of the size of the input image. Let's continue the implementation of our autoencoder. We can keep that one. So we have these separately, the encoder and the decoder. You can just copy either one, call it autoencoder, and its decoder will be basically the decoder with the latent dimension, and its encoder will be encoder with the same latent dimension. And for the forward function, x, well, let's say z becomes self.encode x, and y becomes self.decode z. Let's return y and z itself. Cool. Okay. I guess there is nothing else but to train our network. And actually, let's define our global variables. Let's choose a latent dimension of 384 for cipher 10. Create our model. Move it to our device. What is our device? Well, if you have access to a GPU, which you should, our device is a CUDA device. With this command, we copy our model created on the CPU to our VRAM. I believe the simplest way to train our model is just to have a basic implementation for the training, and then we will add some cool stuff that we can get better results with. So first, let's define how many epochs we want to train our model. So that is a number that represents how many times the model sees our input data. So with 1000, it will see the cipher10 database, the images in it, 1000 times, and it will adjust its weights 1000 times. So basically 1000 iterations of learning phases. And our learning rate, let's set it as a small number. Yeah, around. We will see how it goes. So remember, from the beginning, we have our data loaders, and we can pull batches of input-output pairs from that data loader. So let's define the outer loop first for epochs. So I goes in the range of 1 to epochs plus 1. And for each epoch, we take xy pairs from now actually, as I mentioned, we don't need the y because the y is a class label here. So x is an image of a cow and y is a string saying that it's a cow. So we don't need that. We will have our own y, which will be x itself, because we are reconstructing the input image. Detach just means that let's copy x and unwire it from the PyTorch graph, so we don't calculate the gradients on x. Now these two batches of images, because remember these are not single images, but we define the batch size to be 64, so it will take 64 images from the train data loader, and now we have to copy both to the GPU. So x equals x to our device, and same goes for y. Okay. There's nothing more to do than run our model with the input. And initially, of course, this will be garbage. So we have to compare our predicted y to the actual y with a loss function. Let's say use f, the mean square error loss. So the input is ypred and the target is y. And we can leave all the other parameters as they are. Now that's not going to be enough in itself, because we need an optimizer that actually trains the model itself. Let's use Adam. The parameters are model.parameters, and the learning rate let's move this below so we have our constants here is LR. Okay, as you can see, we can print our model parameters like this. Not actually print, but pass it to Adam, and now I want to print it before the training. So num_params is, we can take p.numel for p in model.parameters. So this will take the number of elements in the model parameters, and we sum those up. So this way we can print the total parameters of our model. Usually this is a big number, so we can divide it by 1,000,000, print it nicely, and that should look okay. So we calculated our loss. Now we use our Adam optimizer First, we zero out all the gradients in our model from any previous steps. And calculate the gradients via backpropagation to all of our layers. And we can step our optimizer. But somehow we want to keep track of how our model is learning, and maybe print the progress in each epoch. So let's create an array called losses, and append the loss from each batch to the losses. And after each epoch, we could print it. But remember, we have, for example, 1,000 epochs. In our case, actually, 100 will probably be enough. But if we don't want to print after every epoch, we can print, for example, every 10 epochs. And after the last epoch as well, when the model finishes training. So epoch number I and how to print the loss. Let's print the mean loss for each batch. Not for each batch, but for all batches. So we have a losses array. We can create a tensor from it, like this. And we can take the mean of it. Yes. This will be the average train loss. Great, that's nice, but we don't actually want to memorize our training data. We want our model to be able to recognize new data that it has never seen and perform good on that. So, as I said, the Cypher10 dataset contains 50,000 train examples and 10,000 test examples. So we used our training samples in this data loader. And we want to also print the average evaluation loss. And this we don't yet have. So let's create a function around here. Evaluate model. And for this, we need to use the decorator torch.noGrad. And switch our model to evaluation mode. But if we switch it here, and we will use this function around this place here, we need to switch our model back into training mode here. So torch.noGrad again ensures that gradients are not calculated as we run our model, because gradients are only necessary for training. Could basically copy this piece of code but run it on the test set instead. These stay the same. The loss stays the same. And we can also create an array here. Exactly the same way as before. we will return the mean of the losses as an evaluation average loss. Okay, let's double check everything. We have our outer loop going as many times as the number of epochs. We have our optimizer wired to the model parameters. The learning rate is fixed. We go through each batch in the training set, only take the input image, and we declare that we want as output the same input image, a copy of it. We move it to our device, we make a prediction with the model, calculate the loss, calculate the gradients with loss.backward, and make our optimizer optimize the model. And then we also calculate the training loss and the evaluation loss. Let's see if I made any mistake and if we can run this training. So it's a pretty small model, a bit more than 4 million parameters. And while it's running into our error, so MSL loss is a tuple. Oh, it's a tensor. So okay, meanwhile, while I have it in my head, let's run model evaluation right before we start training, just to see how our randomly initialized model performs on our data. So initial and now I'm going to fix this error. Oh, right, because when we execute our model, I've decided randomly that we should also return the latent vector. So ypred is actually a tuple. And we're not going to use the latent vector here. So just make a dummy variable there. And we wait. We can perform tiny fixes while the training is running. So while we wait, actually, we can continue further, because as you can see, we calculate the loss twice. But this we might want to change because our results here won't be so fine. What if we just move it into a function of itself? So here we can see that the initial average evaluation loss is 0.065, and by epoch 10 it is 0.03. So it's converging because the loss is getting smaller and the training loss obviously is getting smaller and smaller. Now, one thing to watch out for in here is that when the average training loss becomes much smaller than the average evaluation loss, that means that our model is either too big or doesn't have enough regularization. Basically, it starts to memorize the input data instead of creating a generalized understanding or representation. So it loses forecasting, predicting ability in favor of memorizing the exact input examples. It won't generalize well enough so that when it's faced with new data that is similar but not the same as the input data, its performance will be degraded. I'm not sure how scientific it is or not, but what I like to print out, I just came up with that idea, is kind of an overfitting percentage. So the ratio between the average evaluation loss and the average training loss. Great, we trained our model. So let's try it out. Scroll up and we can actually use this same test data set. And use matplotlib pplot as PLT to display our images and latent vectors for that matter. Now remember, the data set can be addressed, so let's pick an image, for example 700, and that's going to be our input image. We don't need the second part of that tuple because that's the class label. So if image contains a dog, then this will be a string stating that it is a dog. Let's switch our model into evaluation and disable gradient calculation. Print the shape of that image. As you can see, it's 3 by 32 by 32. That's great, but remember, our model expects its input as batches. So our reconstructed image will be actually, we call our model with the image, but we add a dimension to it at the 0 index. So there will be a 1 prefix here, and it will be a batch of 1 image. But don't forget to move it to the device because this is on the CPU, actually in RAM, and we need to move it to VRAM. So we execute our model, and it will return a tuple, not just image rec, but our latent image as well, called Z. It's the latent vector that we compress our initial image to. Now, I'm not an expert in matplotlib, but this way you can show images. However, image and image rec is in the format Let's just stick to printing this image. It has no batch size, and it is in the format channels, height, width. And Matplotlib expects it to be in height, width, and channels. In this case, we can use the permute operation with 1, 2, and 0 parameters. This means that our new dimension here, it will permute the dimensions, so the first dim comes here, which is height. It comes here. The second, width, it comes here, and channel, which is the 0th here, comes as last. Oh, we have a horse. Let's try something else. Can we have a dog? No, it's another horse. A ship. I'm not even sure what this is. That's getting worse, man. I'm pretty sure once I found the dog, but I cannot recall. So, oh, we have a cat. Cool. Let's reconstruct this cat. So this is our input image, and we have a trained model that reconstructs the cat. So similarly, let's show our reconstructed image. The same way, except don't forget that this image is returned like this, because this here is the batch size. This is what is returned from our model. So first we can squeeze it to remove that extra dimension at the 0th place. And this is on the GPU in VRAM. So we need to copy it back to our RAM. And when we have that, we can again call the permute and show it. As you can see, it's a bit blurry, but kind of resembles the initial image. So how does this look like in our latent space? We have Z, our latent vector, and we can show that as well. But remember, that's a one-dimensional vector. So we don't need to squeeze it. We move it to the CPU, and we can view it as, for example, our latent dimension was 384. So let's make the height 16, and whatever is left, this -1, will calculate the rest. And this is actually our cat based on our neural network. This is how our neural network represents this cat in its deepest layer. This will be very useful in later models, not especially from this kind of autoencoder, but we will have variational autoencoders, vector quantized variational autoencoders, and we can use this internal representation to actually create tokens from sounds, videos, etc. So for example, video frames can be tokenized this way, and the best of this is that the video frame will be much smaller in size, so the rest of the model will need to work with a lot less data. So actually, this is a really cool optimization that you can use in front of your models, so that the later parts became much more highly performant. All right, guys, thanks for watching the video. I hope you liked it. If you did, then please click like. Subscribe to my channel if you are interested in more similar content. And please leave a comment if you'd like to join my free Skool community, which is not yet ready, but if there is enough demand, then I will make it. In that, I would like to work together with you on similar projects. And in fact, more complex projects, because this is just an introduction into machine learning. A very simple example. And it's not a secret that I plan to implement Google's Genie. Well, not that Genie. Not Genie 3, Genie 1 in particular has its research paper online published, and it uses a vector quantized variational autoencoder. So as a next step, I'll probably make a video about how to implement that. Then we'll have to talk about transformers, spatiotemporal transformers, and by time building it component by component. If we are lucky, then we can create something similar on a much smaller scale, but something that actually works. So yeah, thanks for watching and see you. Bye.